Okay, so now let's continue our discussion of CPU scheduling algorithms. Okay, in the previous makeup lecture, we talked about the scheduling criteria, and we have looked at our first scheduling algorithm, first come first served scheduling, and we have talked about that this although this scheduler is really simple to implement because we can just implement it by using a FIFO queue as the ready queue. But it has this problem of a convoy effect, right? What it means is that when we have a short job that is scheduled behind of a long job, and we get a really bad average waiting time. Okay? But if we can instead schedule the short job first before the long job, then we can get much better average waiting time. Right? I also give you some real-world examples that I'm sure all of us have experienced at a certain point as examples. Okay? So this brings us to the next scheduling algorithm, shorter job first. Okay, that this is based on the principle, right, the instinct, that the intuition, right, we had from the first come first serve scheduler, the problem with the first come first serve scheduler, right? So we want to schedule short job first, okay, and the most typically when we're considering a set of processes. The shortest job first, or SJF scheduler, will schedule the process with the shortest next CPU burst. Okay, it will schedule the shortest one first. After that is done, finishes this execution on the processor, finishes burst on the processor, then we'll schedule the next shortest one. Okay. Consider all the processes with the long parameters with long CPU burst durations. The SGF, okay, the shortest job first, is in fact the optimal scheduler. Okay, what it means is that it will give us, it is guaranteed to give us the minimum average waiting time for a given set of processes, assuming we already know the CPU burst durations. So you might have heard of or learned about greedy algorithms, right? If you have learned it in your algorithm course, you have heard it somewhere. Then SGF is in fact example greedy algorithm, and because it always is really greedy, right? The way that it works is really greedy. Every time it needs to schedule, you just find the one with the shortest CPU burst. Okay, that's how typical greedy algorithm works. And greedy algorithms are not always optimal. Okay, some of them are. Okay, and the SGF is in fact a optimal one. Okay. And so it just works optimally in CPU scheduling. So, but although it's optimal, but the problem is that we don't know, right? So how do we know the actual CPU burst of the process that we're considering? Before we run the process, we don't really know how long it is going to use the processor, right? So we don't really know the future. There's no oracle which can tell us what is the next CPU burst, right? The length of next CPU burst for a process. Okay, so that is a problem of using SGF. But that doesn't mean that SGF is just meaningless in practice. Okay, because there are ways we can predict the future. Okay, even we don't really have our oracle, but we can try our best to predict the future. Okay, so we will talk about how to do that shortly. Okay, before that, let's also do a simple example. Using the Gantt chart and some example processes, and calculate the average waiting time. Now, in this example, okay, we have 4 processes, P1, P2, P3, and we have we already know their CPU burst times. Okay, 6, 8, 7, and 3. Okay. Now consider these 4 processes, and when we run the shortest job first scheduler. Okay, so then which one should we schedule first? Right, we should schedule the process with the shortest CPU burst. Right, considering all the 4 processes, the one with the shortest CPU burst is P4. Okay, so we schedule P4 first. Okay, start at time 0 and finish at time 3. Now P4 is done. Right, P4 the CPU burst that we need to schedule for P4 is done. Okay, it may come back later, but it's not our concern in this example. Okay. Now consider P1, P2, and P3. Which one should we schedule next? It should be P1, right? Because P1 has the shortest one comparing all the 3 processes. So we schedule P1 next, and P1 finishes in 6 units of time. Now we have only P2 and P3 left, right? So then we schedule P3 next, and P3 finishes at time 16. And finally we schedule P2, right? It finishes in 8 units of time. Now based on this schedule, then we can again calculate the average waiting time, right? Which is so P3 waited 3 time units, P1 waited P1 waited 9 time units, and P3 waited 6 time units. Let me see, and the P4, right? So this is P1, okay. 16 is P2, 9 is P3, right? And P4 weighted 0 time unit, right? So we add them up and divide by 4, which gives us 7, right? Seems to be pretty good, right? So you can run some other schedules on your own, okay, and compute the average waiting time, and to check whether this is really optimal one. We can prove it, but you can also try to see whether you can find a counter example. But I don't think you can find one, right? But you can still try it on your own, just as an exercise for calculating average waiting time. So SDF is indeed optimal. But we said the challenge is that how do we know the future? How do we know what is the length of the next CPU burst? Right? We don't know that, right? And we don't have an oracle that can predict it. So we can only estimate it, right? So whenever we say prediction, we try to predict. Well, we are trying to estimate it. Okay, we're trying to give our best guess. Okay, so how do we predict it, right? Here, let me introduce a simple forecasting algorithm, which is called exponential smoothing. So there are many different kind of prediction or forecasting algorithms. Okay. And really what we are trying to do is to use the past to predict the future. Right? Really, that's the next best thing to do. Right? That's the next best thing to do when we don't have an oracle which can tell us what it is exactly the future. Okay, we use the history to predict the future. Okay, so in this context, in this example, right, we're gonna use the observed lengths of CPU bursts in the past, right? The observed length of CPU bursts happened in the past for process to predict the CPU burst of this process in future. Okay, so so essentially what we have is that we have this process, let's say PI. Okay, and as we run the process, okay, then we can observe this process CPU burst. Right, so T1 would be the process CPU burst, the first CPU burst. And T2 would be this process second CPU burst, okay, and so on and so forth, okay. And then we have Tn, which is this process nth CPU burst. And given all this history, okay, we will try to predict this process, this CPU burst at time n plus 1, okay. And then we use this variable tau to represent that, okay. So tau subscript n plus 1 is this process Pi's length of the length of this process Pi is n plus 1 CPU burst. Okay, so that's the idea. And that's basically how we do prediction. Okay? Use history to predict the future. Okay, and this is a really simple technique, and it's actually used quite often. Okay, in operating systems or in computer systems in general. Okay, when we need to manage something, okay, based on demand. Okay, and here we are trying to optimize the CPU scheduling based on the processor demand of the processor. Right? Later on in the semester, when we are into the memory management part of the textbook, okay, we will see another example where we use the history to predict the future for page replacement. Okay, that is the context. That is the case when we do not have enough physical memory to store all the data that we want to keep in the memory. So we have to decide when we need to bring some new data into memory, we have to decide which data to kick out of memory, right? So that's more like a space management problem. Right? So here, when we talk about CPU scheduling, we are considering the time management, right? So we are doing time sharing of the processor. Now, in memory management, a more important problem is space management, okay, because we have a limited physical memory and we have a lot more data that we want to store. Okay, so how do we manage that, right? And that brings up the replacement problem, and there we use an algorithm which is called ARU. Okay, least recently used the replacement algorithm. Okay, and it's also based on this technique of using history to predict the future. Okay, so we're gonna learn that later. Okay, and I can tell you another example. Okay, which is actually used by one of the two papers that my students are presenting at this conference, which I'm attending this week. Okay, so I mentioned this conference called FAST. It's organized by Usenix. Okay, Usenix is I would say the most important professional community in the IT industry. Okay, and the FAST is the #1 conference in the storage field. Okay, and all the researchers and practitioners from academia and the industry would come together to this conference and share the latest and top results. Okay, my students are presenting 2 papers, and one of the 2 papers is actually also use forecasting algorithm, okay, to manage something. Okay, and specifically that paper is about the management of non-volatile memory and solid state storage based caches. Some of you went to my talk. A couple of weeks ago, I gave a talk to the whole school. Right, the talk is about the title of the talk is all about cache. Right, so that talk is about how to use solid state storage as caches. Okay, and one of my student paper is about that. Okay, so the problem we are facing is that we have a limited capacity, right? So it's also a space management problem. Okay, we're not looking at the space management of main memory anymore. Right? That's obvious. That's a classic problem. It has already well studied. Now we are looking at the space management of solid state storage based caches. Okay, still we have a limited capacity, and then we have a number of workloads that need to share this capacity. So ideally, we want to allocate this limited cache capacity to the workload based on the actual demand, right? So then we have the same problem as the CPU burst problem that we have here, right? So how do we know what is workload's cache demand? Okay, what is workload demand for cache capacity? We don't know, right? We don't know the future. There's no oracle which can tell us that. So the next best thing we can do is to use the history to predict the future, right? So exactly, especially what we do is that we use the observed cache demand of this workload happened in the past to predict this workload's cache demand that's going to happen in the immediate future. Right, so you see that the same principle applies, right, to the loop problem that we are addressing. Okay, for solid state cache management. Okay, and in fact we also use this simple algorithm that we are looking at here, exponential averaging. Okay, by the way, it's also called a exponential smoothing. Right, so if you see this name, it actually means the same thing. So we actually use the same algorithm. Okay, it's slightly more advanced. Okay, slightly more advanced than what we are looking at here, but the basic idea is still the same. Okay, so and it actually works pretty well, right? So hopefully after we learn this algorithm, this forecasting algorithm for the purpose of predicting the length of the speed burst, then you can also understand. You can also use it to solve other problems that you may face in future. Okay, so now I have give you some examples how we can predict the future. Okay, and that is like I said, like I mentioned in those examples, this is quite often used. Okay, whenever we need to manage something and we want to do it on demand and we don't really know the demand, then we can always use the history to predict the future. Okay, to predict the future demand. So now come back to exponential forecasting. Let's see how it is used. Okay, to predict CPU burst. Okay. In our problem. Okay, so I already explained. So T, right? So Tn, okay, which Tn represents the actual length of the nth CPU burst of this process, right? That is observed actual length of the nth CPU burst, and the tau subscript n+1 is the predicted value, the predicted length of the next CPU burst. Okay, which is n plus 1, which is at time n plus 1 for this process. Okay. So then with this, right, then the predict the equation of the used by exponential smoothing is as follows, right? So the predicted length of this process, the next CPU burst, okay, at time n plus 1 is a weighted sum. There is a weighted sum of the observed actual length of this process nth CPU burst and the predicted length of this process nth CPU burst. So how do we understand this, right? So what happens is that we have this series of observed lengths of this process CPU burst, right? And while we are observing this CPU burst, we can also run prediction, right? So given T1, we can predict tau 2, right? And given T2, we can predict tau 3, right? And so on and so forth, and then we have tau n, okay? And then given tau n and Tn, then we can predict tau n plus 1. So that's essentially what this equation is giving us, okay? Now then, when we actually run the process, okay, at the time n plus 1, then we're gonna have T n plus 1, that is observed length of this process n plus 1 CPU burst, right? And then given these two, then we can predict tau n plus 2, okay? So that's basically how this forecasting algorithm runs, okay? Now let's look at a real example that will make it easier for you to understand. So let's look at the two time series here in the bottom of this slide. Okay, so the bottommost one is tau, is the time series tau n, or tau subscript I. Okay, so the first one would be, let's say the first one is if we start from T0. Okay, from 0, then this is tau 0. Okay, so this is the initial value given by the prediction, right? This is the initial value because at the time 0, okay, we don't have any history, right? We have not observed any past CPU burst yet, so we have no history at all for this process. So we have to set the initial value somehow. Okay, we can randomly choose it, okay, or we can do it based on some existing knowledge. Okay. Not knowledge for this particular process because we don't have any history for this process. Right? But maybe we have, for example, just give you an example, maybe we have history for other similar processes, right? And then we can use the statistics about the other similar processes to set the initial value of this process. For example, we can use the average CPU burst length of the other processes as the initial value for this process, right? So that you just make our initial value closer to the actual behavior of this process we are considering here, right? So there are different ways to set it, okay, but here let's just assume we set it somehow, and the initial value is set to 10, okay? And then given tau 0, which is 10, and let's see, and then we actually run the process, right? When we run the process, then we get T0, okay? That is the amount of time that this process actually spends, right, at time 0 on the processor. Okay, so the row above the bottommost row is T subscript I. Okay, so this is this time series of the actual observed length of the CPU burst. Okay, so now with the T0 and tau 0, okay, then we can calculate this is tau 1. Okay, so how do we calculate tau 1? Tau 1 equals to alpha, okay, times T0 plus 1 minus alpha, okay, times tau 0. Okay, so and in this example, I believe alpha equals to 0.5. Okay, so then we have 0.5 times T0, okay, plus 0.5 times tau 0. Okay, and let's substitute the variables with the actual numbers. We have 0.5 times T0, which is 6, plus 0.5 times tau 0, which is 10, right, which gives us 8. right? So that's how we calculate tau subscript 1. And then we run the process on the processor again, right? And then we can observe T1, which is 4. And given T1 and the tau 1, then we can calculate tau 2, okay, which is half of 4 plus half of 8, which gives us 6, right? And then with tau 2, then we can again observe T2. Okay? Given T2 and tau 2, we can estimate tau 3, and so on and so forth. Okay, that's basically how it runs. So then we can put these two time series on a diagram, okay, which is the diagram showing here on this slide, okay, and to see how they match each other, right? Are the predicted lengths actually match the actually observed lengths? On this diagram, the x-axis is time, right? So we start from 0 and 1, okay, and so 2, 3, 4, 5, 6, 7, 8, 9. Okay. On the y-axis, we have the values of predicted length and observed length. The black line here is the actually observed length of the CPU burst, and the blue line is the predicted ones. At T0 we have, let me read this one. At T0 we have the predicted one is 10 and the observed one is 6, right? And T1, the predicted one is 8, observed one is 4, okay, and so on and so forth. Okay, so when we look at this diagram, we can notice two things. One is that at the beginning, right, initially there may be big difference, right? Especially at time 4, there's a huge difference between the observed one and the predicted one. Right? But it basically initially we may have a big difference between the observed length and the predicted length. But as we run the algorithm long enough, these two curves they converge. So why? Because when we run the algorithm long enough, we have enough history, right? We have enough history to predict the future. At the beginning, we do not have enough history. We do not know about this workload long enough, right? So our prediction may be off. But after we collect enough history, we have observed enough pattern of this workload. Our prediction will get better and better. Okay, so that's generally what happens, okay, when we do forecasting. It is just like when we do weather forecasting, right? So like a couple of weeks ago, it was really hot, okay, and we were close to like 90 degrees, right? And when you check the weather forecasting, you can also see what is the historical range of the temperature for that period of time in a year. Right? So most of the time, generally speaking, when we don't have any special phenomena happening, like the El Nino, that's what is happening, which is giving us a lot of rains, right? But generally, when that is not happening, then the prediction should not be that off. Okay, so when the history says we are between, say, from 60 degrees to 80 degrees, then that's generally what the temperature should be. Right? So that is basically what is happening here. Okay, with enough history, and we'll be able to understand the pattern of the workload, and we'll be able to give a good estimate of the future. Okay, and that's generally the case. Okay? And that's what's happening here. That's one observation we can make. Okay? When we have enough history, we can give a pretty good prediction. And the second observation we can make is that you can see. So when you look at the blue line, you can see how smooth it is, right? So this algorithm, this exponential averaging algorithm, actually has this smoothing effect. That is also why it's also called exponential smoothing. Okay, so that's how this algorithm works. So let's talk about a little bit more about this algorithm. Let's try to understand fundamentally how it works a little bit better. Let me write down this the equation of this algorithm again. So what we have is tau subscript n plus 1, which is the predicted value of a CPU burst at time n plus 1 equals to Tn, right? Alpha Tn, let me write alpha first. Okay, alpha times Tn. Tn is the observed length of the nth CPU burst plus 1 minus alpha times tau n. Okay, and tau n is the predicted length of a time n. Okay, so that's the equation. Okay, so here let's try to understand the importance of this parameter alpha. Okay, so so basically what happens is the alpha will decide how much weight the history will give, okay? How much weight, how much contribution the history will make to the predicted value. So generally speaking, I think the higher the value of alpha, the more important the history will have, okay, to the predicted value. Okay, so let's look at it first. Let's look at some extreme cases. Okay, so if alpha equals to 0, okay, then what happens is that then basically this term becomes 0, right? So what we have is just this. Okay, so what it is saying that the predicted length of the next CPU burst equals to the predicted length of the current CPU burst. Okay, so in other words, history doesn't matter, right? Because the history doesn't even show up in the equation anymore, right? We are just using our guesses, okay, to make our guesses. So this is a really extreme case. It doesn't, it's not really meaningful, okay, because the reason we want to use exponential smoothing is because we want to use history, right, to some extent. So this is just extreme. I just tell you, so when alpha is really small, right, when alpha is close to 0, then we're not considering history at all, okay. So the lower the value of alpha, the smaller impact the history will have to the prediction. And on the other hand, right, to the other extreme, if we set alpha to 1, then this term becomes 0, right? Then all we have is this. Okay? So this is actually 1 now, right? So we have what we have is that the predicted value of the next, the predicted length of the next CPU burst equals to the observed length of the previous CPU burst. And we are only considering, in this case, we are only considering only the most recent history, which is the last value, right? So we are not considering t n minus 1, we're not considering t n minus 2. We are only considering the last most recently observed value of the CPU burst. Okay, so that's also why when we set alpha to 0, when we set alpha to 1, okay, we also call this as last value based. So essentially, we are just using the last observed value as the next predicted value. Okay, last value. The observed length of the last CPU burst as the predicted length of the next CPU burst. Okay, in the context of our problem. Okay, so then, but in general, right? So when we set alpha between 0 and 1, then we can expand this equation. So what we get is like this. Okay, again, everyone know how to expand it, right? So we will get like this. Okay, you can see, so you see that the predicted value of the next CPU burst, tau subscript n plus 1, is a weighted sum of all the past history. Okay, given the coefficient, okay, calculated by alpha and the 1 minus alpha. So the weight of the last observed value is alpha, and the one before last one is alpha times 1 minus alpha, okay, and so on and so forth. Because alpha, both alpha and 1 minus alpha are less than 1, right, or equal to 1, right? So this coefficient is less than alpha, right? So this coefficient is less than previous one. So what this tells us is that as the further we are into the history, the length impact that history will have to the prediction, which makes sense, right? Because the older the history is, the less representative it is for this workload's current behavior. Only the recent history, have better representation, can better represent this workload's current behavior. That's what they basically say. The further we go into the history, it is less representative of the workload's current behavior, and the observations happened at that time, taken at that time, should have a less weight, should have a less impact to this workload's next lacks the CPU burst. Okay, that this workloads lacks the CPU burst in that. Okay, that's basically what I say. Okay, and this is the basic idea for exponential smoothing. Okay, and again, so even in this equation, right? So if we set alpha to 1, if we set this to 1, right, then all these following terms are gone. They're all 0, right? So they're gone. So basically, we are considering only the most recent history, which is the last value. Right? So now you understand what alpha means. So alpha with this coefficient alpha, will be able to give the history weight. The older the history is, the less weight it has to the prediction. And the larger the value of alpha, the higher weight the history has. And the extreme case, when the alpha is to 1, the only last value matters. In the other extreme case, which I said is not really meaningful, when alpha is set to 0, then we will not really consider any history. Okay? But generally speaking, when alpha is smaller, all the history have a less impact, okay, to the prediction. Okay, and this is really useful forecasting algorithm. So I've spent a little bit of time helping you understand it, and I hope it can be useful for you to solve other problems. Okay, not just this. In this context, we are using to predict the length of the CPU burst, okay, of a process. In fact, you will find it useful for project 3, okay, which is a project on memory management. Okay, of course, we're gonna talk about that later. Okay, so let me stop here. I think it's already 30 minutes. So let me save my video and upload it, and we'll continue in the next video.